This is the title slide for CSE 153, Design of Operating Systems, Winter 2023, Lecture 4 on Processes. Last class covered OS structure, operation, and interaction with user programs, focusing on privileged mode and system calls. The OS primarily runs in response to events, scheduling user processes and then going to sleep until another event occurs. Events can be categorized as synchronous or asynchronous, and as unexpected faults or deliberate system calls or signals. The diagram illustrates a system call initiated by user mode code, trapping to kernel mode to execute the read kernel routine, then restoring state and returning to user level. This slide presents another view of memory layout, showing kernel stack and code, along with user stack and code. A timer is a key component for time-sharing operating systems. It generates interrupts, allowing the OS to reclaim control and form the basis for the scheduler. It's also used for time-based functions like sleep. The OS provides abstractions such as processes, file systems, and virtual memory to applications, virtualizing hardware like the CPU, disk, and RAM. Virtualization provides each program with the illusion of having its own copy of resources, freeing them from managing sharing, which the OS implements. This lecture segment will cover processes, threads, and synchronization, which are fundamental concepts for the midterm and Project 1. We will discuss the virtualization of the CPU and the representation and scheduling of applications. The process is the OS abstraction for execution, serving as both the unit of execution and the unit of scheduling. It represents a program in execution, including dynamic state and resource ownership. To support the process abstraction, we'll examine the state a process encapsulates, process behavior related to CPU time sharing, OS data structures and scheduling roles, and the process interface offered to programs. A process contains all the state for a program in execution, including an address space with static and dynamic memory, control and general-purpose registers, and OS resources. Processes are named using their process ID or PID. The address space of a process is a memory abstraction that includes the stack, heap, static data, and code segments. To support the process abstraction, we'll examine the state a process encapsulates, process behavior related to CPU time sharing, OS data structures and scheduling roles, and the process interface offered to programs. A process exists in various execution states, running, ready, and waiting, reflecting what it is currently doing in relation to the CPU and system events. As a process executes, its state changes. Unix PSX command reflects this in the stat column. This is a diagram of the execution state graph. Processes can be new, ready, running, waiting or terminated. To support the process abstraction, we'll examine the state a process encapsulates, process behavior related to CPU time sharing, OS data structures and scheduling roles, and the process interface offered to programs. To support the process model, we will discuss how the OS represents a process in the kernel, how it pauses and restarts processes, and how it tracks all processes. The process control block, PCB, is where the OS stores a process's hardware execution state when it's not running, including process ID, execution and hardware state, memory management details, scheduling info, accounting data, and pointers for state queues. This slide shows the XV6 structure of proc. This slide details the Solaris struct proc. This slide continues to detail the Solaris struct proc. This slide completes the details of the Solaris struct proc. To pause or restart processes, the OS saves the hardware registers to the PCB when a process is stopped and loads these registers to the hardware when a process restarts. Changing the CPU hardware state from one process to another is called a context switch.